Hello everybody, it's my pleasure to welcome you to the Department of Physics and to tell you why I think physics labs are important. So if physics is about understanding the natural world by building models, which allows physicists to make predictions, check hypotheses and draw conclusions, these physics models really need to be constructed from a combination of theory, computation and experimentation. So in your lectures, you'll be learning a whole bunch of physics theory and how it's applied to different models of the natural world. And the main tool of physics theory is mathematics. The laboratory course, on the other hand, has been designed to teach you the tools of experimentation. And the advancement of science through history has relied on the very careful observation of nature. Very careful observation. And so modern experimentation in physics relies on the communication of the results from experiments in ways that others can understand and use. Therefore, the expression of the quality of the result from an experiment is at the heart of experimental physics. In this department, the research interests of the physicists span the entire length scale of the universe, from particle physics to nuclear physics to nanoscale physics to solid-state physics, all the way up to the flow of material in bulk, applied physics. We are participants in both the ATLAS and ALICE collaborations at CERN, and within the R.W. James building, you'll find research laboratories for nuclear physics and for nanoscience. This year, the coldest place in Africa will come to our departments when we buy a 10 millikelvin refrigerator. Yes, 10 millikelvin for material science research. We have close links to Itemba Labs, National Laboratory, where there are facilities for nuclear physics research, both pure and applied, using particle beams from a cyclotron, and also for industrial flow studies where we use modified PET scanners for that work. Our theoretical physicists model the conditions of the early universe in order to understand the very nature of nature herself. We also have research programs into the teaching and learning of physics. All this research relies on the understanding of the results from experimentation. For example, the Higgs boson would not have been discovered without very careful consideration of the quality of the inferences that could be made from the data. Therefore, in your lab course, you'll be asked to think very carefully about the quality of your experiments and taught ways of expressing that quality. Fortunately, there are international standards regarding the expression of measurements and uncertainty in science. By uncertainty, we don't mean mistakes, because if you made a mistake, you just simply fix it. Uncertainty allows you to express the quality of your measurements in ways that others can understand. This expression is done in a standardized numerical way. A measurement result is thus an expression of what you know about what you set out to measure. Since this knowledge is never perfect, the result of a measurement is never a single number. If it were a single number, that would imply that your knowledge was perfect, and that's never the case. The result of a measurement is therefore always expressed as an interval. And the width of this interval is an expression of the quality of your result. So this year, you'll be taught about all that, and you'll also taught the technical stuff that goes around that as well. So please remember that the technical aspects are not the most important thing. They are important, and you do need to learn them, but we really need you to understand why you're doing what you're doing. So ask questions, often. Call demonstrators, speak to the academic staff. The department wants your lab experience to be really enjoyable, and if it's not, please tell me about it and we'll fix it. So have a good semester, don't fall behind. If you do, there's very seldom a chance to catch up, so keep up with the good things, and my best wishes to you all.